now we will look at another storage system, and the reason we picked this storage system is because it is completely opposite of Raft, right, in the design space. So in particular, we will look at Amazon's Dynamo. Right, so let us see what is the problem that Dynamo is trying to solve. So Amazon receives a lot of small writes, right? So you add one item in the shopping cart, right? You change your password. So Amazon is receiving lot of small reads and writes, and you want to get high availability, right? So reads and writes should succeed 99.9% of the time in less than 300 milliseconds, right? This is the goal they have set up for themselves, right? So you want almost all reads and writes to succeed quickly, right? The system that we saw, Raft, can it offer this? Right, so Raft tends to become unavailable at times, right? So maybe during some term there was no leader, so no one can accept writes. But in general, consistent systems cannot be available during fault tolerance. So this is called CAP theorem, right? So when there is network partition, sorry, not fault tolerance. When there is network partition, you can either choose to be consistent or you can choose to be available. So let us see what this means. Let us say we have two replicas and there is a network partition, right? Both of us think that k, the value of k is v, and someone comes and tries to change k to v prime. So now there are two approaches we can take, right? So one approach is taken by Raft, right? So Raft says that I will not return to client until I can form a majority, right? So I will make sure that I am always consistent, right? So I will not return to client. To client I will say failure, because when I was trying to update v prime, I was not able to update my replica, right? So the system becomes unavailable, right? It cannot be written. So in Raft, this can be the minority side, right? The minority cannot accept updates because it cannot form majority, right? But in highly available system that prefer availability, you may say that, okay, write has succeeded and the value of k is now v prime, but you end up with inconsistent data, right? So here we preferred availability, that I never want to reject writes. I always want to make sure that writes succeed. Here we are preferring consistency. I never want to diverge, right? I want to make sure that my system always behaves in a consistent manner. And we defined the notion of consistent as sequential consistency, right, for Raft. If you start doing this stuff, then you will start breaking sequential consistency, right? There has been an extension to CAP theorem called PACELC theorem. This is just so what the first three letters are the same. What this says is, at the time of partition, you can either choose availability or you can choose consistency, or else, that means there is no partition, you can either choose consistency or you can choose low latency, right? So consistency has this overhead that I have to form a majority, get back ACK from everyone, only then I will move forward. Whereas if you don't worry about consistency, then you can get even lower latency, right? Because I can just return immediately without forming majorities. So Dynamo prefers availability over consistency, right? So we will happily become inconsistent. But the main goal is we want to be available, right? So writes should never fail. From the point of view of clients, Amazon is always available, right? That is the goal. So of course, this will not work for financial transactions, just like we saw in morning, right? But it makes sense for Amazon, right? So if someone is trying to add milk into their shopping cart, let them add milk, right? So that is the goal. So the the interface is pretty simple. It's just a key value store. So availability is saying that rights are not rejected, that the system will accept your rights, right? So here in this scenario, this right was rejected, right? Because it was not able to form majority and it rejected the right. So availability is saying that don't reject anything. From the point of view of the client, you can always accept reads and writes. Latency is something different. Latency is you want to be quick, right? Quick in responding. Okay, so the interface is pretty simple. Just a key value store. There are many ways Amazon uses it. For instance, key is user ID and value is a blob containing the shopping cart, right? So to add something, you get the shopping cart, you add milk in it, and you put the shopping cart back for the user, right? So very simple interface. So again, the requirement is even when data centers are being destroyed by tornadoes, you should continue to accept rights, right? You should never say, this is the example that they give in the paper, in the first paragraph of the paper. But even though data centers are being destroyed by tornadoes, you want to let people continue shopping. Okay, so data centers are being destroyed by tornadoes. So we don't want any master, right? So in Raft, we had a leader, and the leader was the only one who can take rights, right? But if the leader is getting destroyed, this may add latency, so we don't want any master, right? So we will build a completely decentralized storage system. There is absolutely no master. Okay, so since this is the first time we are looking at decentralized systems, we should do it in two halves, right? So we will first try to build a read-only key value store, right, where you just try to get keys, right? And once we figure out read-only key value store, then we start writing and then dealing with inconsistencies. So master was pretty useful, right? If you think about, so if we, so now we have bunch of servers, right? Some servers are holding some keys, right? So if you have master can do load balancing, right? So it can check which server is taking how much load, and if some servers are getting busier, it can move certain keys to someone else, right? If it can also do failure detection, right? So it can, we discussed in MapReduce, it can do heartbeats with everyone, and if some storage systems are dead, then we can detect that. Then master can also do addressing, right? So clients can go and ask master that I want this key, and the master can say go to this particular server, right? So there are all these nice benefits that are easily solved when we have a centralized service, right? Because master can take care of a lot of these things. But now we would like to do all of these things without having any master, right? So we would want to do load balancing, failure detection, finding out where is the key without any master. Okay, so the first problem is, let us say we have bunch of keys, we have millions of keys, right? And we want to figure out who has those keys, right? So let us see how we should basically split the keys. So we have millions and even more keys, and we may have 100 to 1000 replicas, right? And we want to split these keys in a decentralized way and yet do load balancing.
Sir, but given the fact that we are not bothered about consistency now, why should we care about this? I mean, if someone's asking for a key, we can just randomly invent a value and give it, right? That's good enough. We don't care about consistency now. So.
That is a very interesting point. So the point is, I build a system that when reads X always returns 42, right? Right. So every shopping cart you read, you get milk or whatever. So we don't care about sequential consistency that we cared about in Daft, but we still care about sanity. So I don't know what is the right word here. Maybe there is an academic term here, but I mean, if I didn't add anything to my cart, I shouldn't see it, and right. Otherwise, what are we doing? But I don't know what is proper way to define it. So one way to define it is I should only get back 42 if I wrote 42. If I never wrote 42, why am I getting 42 back?
Is this a correct principle?
Yeah.
So sequential consistency means that write shouldn't appear out of order.
Yes.
There cannot be any we cannot read something that was not written.
Right. Right.
So then the last problem you mentioned about when we had that master, it was able to find out, where if you ask for a key, it was able to do the addressing of which of the servers it contains. Why is that problem a relevant problem now?
Because even now you have millions of keys, millions of Amazon users, right? And when a user wants to change their shopping cart, you want to insert that. So you want to add milk, right? How do you have to first locate where is the shopping cart, right? Any other questions? Okay, so any thoughts how to do this? So the problem is we have millions of keys and we want to figure out for a given key who has the data for it.
Store like a map from keys to like server.
Right. So the first idea is we will keep a map that for key 1, W2, W4 has key 1, key 2 is with W1, W5, right? Every worker remembers where every key is, right? But because we have millions of keys, this can be pretty large, right?
Instead of remembering where which worker contains each key, why can't they instead remember the values themselves? If they are anyway going to be remembering all of those millions of values.
Right. So the argument is this is not scalable, right? So we are not building this, right? Because the routing table becomes large, and if worker 2 crashes, we have to modify so many entries in every worker that hey, I don't no longer hold any keys, right? So the other idea to do this could be hashing. Yeah. So we can hash the key and do some sort of static partitioning, right? So let us say I just have 256 keys and I have 4 workers. So I will assign first 64 keys to worker 1, worker 2, worker 3 and worker 4. Right. So the benefit of this is that the routing information that everyone needs to maintain is much smaller. Right. So I just need to remember 4 entries instead of 256 entries. Right. But if a new worker joins, let us say W5 joins, right? So I have to rebalance this, right? So I have to 204, 51. Right, so I have to rebalance the whole thing when a new worker joins, right? And this affects data on all the workers. So keys 51 to 64 will be sent over to W2 because W2 now owns them. 102 to 128 is sent to W3. 153 to 192 is sent to W4, and 192, 204 to 256 goes to W5. Right. So this is causing data movement on all the workers just because a single worker joined, and it is also causing imbalanced load transfer. Right. So W1 only had to move 13 keys, whereas W4 had to move 51 keys. Right. So the more right you are in this, the more data you have to send out. But the good thing is the routing table is pretty small. So then the other idea, and any other thoughts how to fix?
Fix the size of keys per worker and then add sequentially. Like if 256, 192 to 256 is handled by worker 4, additional 64 would be added. Like
Okay, so your suggestion is to increase the key space.
yes.
So the problem is you have changed the hashing function, right? So every key will go to a new worker now. So this will require a full shuffle actually, right? So what you had before, right? I think this will require a lot more shuffle.
It's kind of scalability. Like if we have more number of users, we are adding more number of workers. In that case, this would work. But if we have like same number of users and then we are adding additional workers, then this would not.
Yeah, so you have some keys that you already had, the system already had, and you're adding a worker. So now if you change the hash function, then every key will have to shift to the new owner, right? So the key that was falling here, because you instead of doing %256, now you are doing %307 on their hash value. This will end up falling somewhere else, right? So lot of keys might have to move because of this. Okay, so the other approach, so the approach is simple, that instead of breaking into 4 components, 4 sections, we will break them down into Q sections. So I will now draw this as a circle. So it is drawing the same thing, 0, 64, 128. 192 and then back to 256. So everything from 0 to 64 was owned by W1. Everything from this to this is owned by W2, W3, W4. Right? So I'm just drawing what I had here. I'm just drawing this as a circle. Right? So another way to draw this is I will write W4 here, W1 here, W2 and W3. So what it means is all the keys that are here are handled by W1, right? So basically 0 to 64 are handled by W1. 64 to 128 is handled by W2. So whenever you are at a location, whoever is the next worker holds the key. So the idea is, instead of creating only 4 partitions, we can create lot more partitions, right? So let us say here we have W2, here we have W3, then here we have W3, here we have W4, here we have W4, W1. Right, so instead of splitting the keys into just 4 partitions, I have split the keys into lot more partitions. So now when W5 joins, the W5 can join in multiple places in the ring. Right, so W5 joins here, as well as here, as well as here, as well as here. Right, so now the data that we need to transfer is that all this data was being handled by W2 before. Now it will be handled by W5. So W2 will send this data to W5. All this data W3 will send to W5. All this data W4 will send to W5, and all this data W1 will send to W5. Right, so this way we have balanced the amount of data that a worker had to pass to the new worker. Right, so W1, W2, W3 and W4, everyone is passing some amount of their keys to W5, and the rest of the keys need not change. Right, so W6 will also sit in 6 places, so everyone will, or 5 places, and everyone will transfer some keys to W6. Okay, so in general, basically Dynamo creates queue ranges. This is called the token thing. Right, queue different ranges in the token thing. When a new worker joins, it steals q by n ranges, right, for load balancing. And the worst case routing table that we have is always O of q. Right, so q is bigger than n. Right. Okay, any questions? So we have figured out where the keys are in a decentralized manner. Not fully figured out where the keys are, but we have figured out how to place the keys in a load balanced manner.
Is this similar to the idea behind consistent hashing?
Yeah. It's similar, yeah. Okay, so now the keys are placed, let us say, right, a worker joined, keys are placed. So now someone says that a client says that who should I ask, where should I read the key from, right? So previously we had master, and W3 is the new guy who joined. It can say I am handling keys from 0 to 64, and master can return that W3 is handling 0 to 64. But now I need to tell everyone that I am handling certain keys, right? So one way is I go and tell everyone that I am handling these keys, right? And by the way, we can also do dynamic load balancing, so the key ranges also changes, right? So if W3 was idle, it can steal some keys from other workers, so the key ranges keep changing over time, right? they don't change in Dynamo, but they change in Cassandra, which was influenced by Dynamo, and the design is pretty similar. So the key ranges keep changing over time. So the problem is, how do you tell everyone what is the key range, right? Without doing this one-to-one broadcasting, right? So every time something changes, I have to tell everyone. So the main idea is, instead of telling everyone, Dynamo uses what is called the gossip protocol. The idea is the workers randomly pick another worker every 1 second and gossips with them, right? So, and what gossip is about when W1 and W3 are talking to each other, they don't just talk about each other, right? They talk about everyone. So gossip is quite useful because W1 if W1 has an update, W2 will get to know about the update made from W1 in the second round of gossip, right? So in log n rounds, right, everyone will get to know stuff about everyone else, right? So gossip is really, really good because the rate at which information can flow becomes logarithmic, right? So how to do this gossip? Let us say W1 and W2 want to gossip. So W1 knows the following. W1 knows that I am handling keys 0 to, or let me just use, I am handling keys from A to B. My current load is 0.5. W1 knows that W2 is handling keys from B to C. Its current load is 1. W3 is handling keys C to E. Its current load is 0.9. And W4 is handling E to A. Its current load is 1. Then W2 also knows stuff about other people. So it knows that W1 is handling E to B. W2 is handling B to C. Its node is 1. W3 is handling C to E and its load is 1.2. Right? So W2 does not yet know about W4. So W4 has joined the token ring and it stole keys E to A from W1. Right? So but W2 thinks that E to B is still with W1. So one way to gossip is all of this information is sent across, right? So when W1 talks to W2, W1 sends everything it knows about everyone else to W2, right? And then W2 updates, right? But that has too much data transfer. So like nothing has changed for W2, right? W2 is wherever it was, but we are unnecessarily sending data about W2. The other problem is, how do we know which update is latest? So is 0.9 the new load of W3 or 1.2 is the new load of W3, right? So if W3 had gossiped with W2 first, then maybe this is the new load of W3. If W3 had gossiped with W1, then maybe this is the new load of W3. Right? So we also need some mechanism to know which is the later data, right? So the mechanism that that is used is to use vector clocks, right? So we will assign a version for every worker. right? So anytime a worker has to say something new about itself, it will increment its own part of the vector clock. So let us say W2's load has changed, or the tokens that it was handling has changed. It will increment its own part of the vector clock, right? And similarly for other workers. So now the way the gossip works is W1 has randomly picked W2 and it wants to gossip with W2. So it doesn't want to send all the information to W2 because a lot of it may not have changed. So instead of sending all the information, it will just send the vector clock. It will say that W1 is at 345, W2 is 63, W3 is 23, and W4 is 39. Right? So it is just saying that I have this information about all the workers. Right? It is asking W2, do you need any information? So worker 1 realizes that its information of W1 is outdated. Right? Its information of W2 is same, but it has new information for W3. So it can respond that I need information for W1 because my version of information for W1 is old. And by the way, the information of W3 has changed, right? And I also need information about W4 because I don't know anything about W4, right? So it sends information about W3 because this is 24 is greater than 23, right? It doesn't send anything about 63 about W2 because the clocks are the same. Then W1 can apply these updates of W3 and it can send what W2 wanted, right? So it can send that, by the way, W1 is now handling A to B, load is 0.5, clock is 345, and W4 is handling E to A. Right? So in just 3 exchanges, we know everything about everyone, or we both of us are updated, right? That's the idea of the gossip protocol. One thing we did not quite touch is fault tolerance in this read-only store. So we should talk about that before we start talking about writing. Right? So for fault tolerance, we still need replication. Right? So the way we can do replication in this token thing is all these keys will be handled by next 3 workers in the token thing. Right? So all of these W3, W2 and W5 will keep copies of these keys. Right? And when you have to read, you can read from anyone. Right? So replication is still required for fault tolerance. The other part is, so we were saying some key ranges may be updated asynchronously. So someone thinks that W1 owns this key, but this key is actually owned by W5 now, or W1 no longer owns this key. So that is also fine. If client comes to W1 and saying that I need a certain key, W1 can say I don't have the key. Why don't you go to W2, W3 or W5? Right? So even if the routing table is a bit stale, we should be okay. Right? Okay, so now we have a read-only decentralized key value store that splits data using this token thing and updates the routing table based on the gossip protocol. Right? So it is completely decentralized. There is no master where you have to register and the master is giving out token ranges and so on. Right? So now we can start writing to Dynamo. Right? And remember, the requirement when we write is availability. Right? So we care a lot about availability and we care a lot about latency. right? And we will prefer availability and latency over consistency. So let us see how write works. So we have the same token thing. Here we have different workers, right? Worker 1, 2, 3. By the way, worker 1, 2, 3, these are just servers, right? These are the ones that are holding the key. So now a client comes and says that I want to write a particular key. Worker 1 will coordinate the write, right? So this will do something similar to Raft to build the majority. Not the majority, but replicate across replicas. And we need that for fault tolerance, right? So if only worker 1 writes and responds, and if it crashes, then we may completely lose the key. So the users of Dynamo can tell Dynamo how many places you want to replicate a key, right? So let us say if users of Dynamo have set W2, then W1 will replicate the key to W2. Once W2 responds, it will return that the key has been written. Okay, so this looks very similar to Raft so far. So remember, just another caveat, that these are close to each other on this logical tokening, right? These workers. But physically they can be very far apart, and they should be far apart, right? So if W1 is in a data center destroyed by tornadoes, right? W2 and W3 are hopefully in a separate data center. Okay, so now let us see how Dynamo responds when it is not able to talk to the replicas, right? So these replicas may have crashed, or they may be unavailable because of whatever reason. And in this case, what Raft would have done is to reject the write, right? I will not write because I may end up with inconsistency. Whereas what Dynamo does is Dynamo will send the update to a new replica, right? And as soon as this replica returns, it will say that the write is okay. Similarly, a client, so also the other difference is Raft, only the leader can accept writes, right? So here, let us say these nodes or workers were actually not dead, right? They were just partitioned from this worker because they are in different data center and there is a network partition between data center. So some client may try to write to the same key, right? And they may send the write request to a different node, right? And in Dynamo, it is allowed for this node to also coordinate the write, right? So it will coordinate the write, replicate it on W equals 2. When the application is done, it will respond that K2 is now V2 prime, right? So we use this both for right? So when there are faults that you are not able to talk inside the 3 replicas, you will write to some other replicas, right? And there is not a single leader, right? There is not a single coordinator who will coordinate these writes. Anyone can coordinate the writes, right? As long as you hold the replica, you can also coordinate the write. So as we can see, this has led us to inconsistency, right? So a client on one data center that was talking to one data center thinks that K2 is now V2, and a client who was talking to another data center now thinks that K2 is V2 prime. Both of them received an acknowledgement, right? But they are different values. So this is not allowed in Raft, right? But this is allowed in Dynamo because we prefer availability, right? We never want to reject writes. right? We just accept writes. Okay, so now the issue is writing is okay. You can write anything if you don't have to read it, right? Doesn't matter. So how to read is now an issue because we let our storage system diverge, right? And now when we read, we might end up reading diverging values, right? So similar to this W flag, uh, whoever is administrating your Dynamo storage can also set a R flag. So R is saying that read from these many replicas before returning me the response, right? So now a client goes and says what is the value of K2, right? This will coordinate this read, and now this time let us say it will talk to, it is able to talk to this particular replica, and now there are two values, V2 and V2 prime, right? So we got two different values from read. So instead of returning a single value, we will return both the values, right? That the value of K2 is both V2 and V2 prime, right? So the approach is basically similar to what we have seen in Git, right? In Git, similar things can also happen, right? So we have a common commit, right? And we have one laptop here, one laptop here, right? They are making writes to their local copies, right? The code has now completely diverged, and then at some point we want to do a merge, right? So this is the same idea that we are going to follow in Dynamo, right? So we are going to let the storage system diverge, and at some point when the replicas are able to again talk to each other, we are going to merge the diverging replicas, right?
So what if there are merge conflicts like there are in Git?
Right. So what if there are merge conflicts? So in programming, we get merging conflicts and we have to resolve them manually, but there is no manual intervention here, right? You cannot suddenly ask an engineer what is the shopping cart of this person, how to deal with that, right? So let us first see how this particular commit graph or his version history is maintained in Dynamo, and then we will come back to that question on how to merge, right? So let us say initially we wrote a value D1 for a certain key, right? And this write was handled by a server called X, let us say. So this server will remember that I am the one who coordinated the write. Then we again write D2 and again X coordinate the write. So X will increment its own counter that I am the one who coordinated this write. Now let us say some replicas are disconnected, right? So someone else will coordinate the write, right? So let us say X was unable to participate or unable to coordinate the write. This time Y coordinated the write. So this is Y is another replica. And someone else wrote D4, and this time some other replica Z coordinated the write, right? So the writes are diverging, right? Now when you try to read and now let us say both of these replicas are again able to talk to each other. When you try to read, you might get both the values back, and then again when you write D5, this is considered as a merge. So how you merge is up to the programmer, but when you write again, this is considered as a merge. So let us say this time this is coordinated again by x. So we maintain a new version, right? So as the writes are going into the system is managing, for every key it is managing multiple versions, right? And these versions can diverge if different replicas are coordinating the writes, right? And later when you read, you will get multiple values, and if you write again, the write will be considered as a merge. How do we like this? Is this?
Can data be lost because of this?
Hmm?
Can data be lost because of this?
So data cannot be lost as long as, so we have set W to 2, right? So for every write, at least 2 replicas have seen the write, right? So if those 2 replicas will come up eventually, that write will surface again, right? But it may happen that you keep making lots of writes, that this client keeps making lots of writes to these 2 replicas without seeing the writes made to this replica for a long time, right? Because we have been disconnected for a long time. So I can keep making changes to data center that is close to me. Someone else can keep making changes to data center close to them, and maybe we are both editing the same key, right? So we will stay disconnected for a long time, but when these 2 data center become connected again, then when we read, we might get 2 values that we need to now reconcile.
And of these two values, we will have to choose only one.
Right. So the question is how to reconcile, right? So one approach to reconcile can be simply a syntactic reconciliation, right? So let us say what I'm writing is, for every user is the key, I'm writing their password, right? So let us say for the same user, I am here in the classroom, I change my password, then I go home, maybe I travel, then but that's a long time, but for whatever reason I change my password from a different location at around the same time. So the password that I have set has now diverged, right? May have diverged. So now, because the 2 data centers could not talk to each other, so one option is you can let Dynamo do the merge automatically by just looking at the timestamp, right? So you can let Dynamo do last writer wins, right? So whoever set the password last wins automatically, right? So instead of returning 2 values, the Dynamo system will automatically merge based on this last writer wins and just give you 1 value. The other approach is semantic reconciliation, right? So here the idea is I have now the same scenario, but instead of password I have a shopping cart, right? So from one location maybe I add onion, from another location I add potato in my shopping cart, right? And when I want to merge, if I let the last writer wins, I will forget about onions, right? So instead of letting Dynamo do last writer wins, which is the default policy, I can let the programmer do something meaningful, right? So programmer can take a union of the 2 shopping carts and write potato comma onion as D5, right? So this is custom handled by the programmer according to their use case, and this is the default, that if you don't want to deal with it, if last writer wins is okay for you, then you can let Dynamo do that. Okay. Any questions?
items in the cart, and we always have to write, if we are trying to increase it by 1, we should not say 2 plus 1, it's 3. Like, you read the value and you do plus 1 and put it.
Right.
If they are doing this one, then these approaches won't even fit.
Um,
You just put the last value. The last value will read, it's not 2 anymore.
Say that again. So you had 2 potatoes in the cart and you are trying to add a potato.
Yes.
Okay.
So if you are doing it from a different location, maybe there are 2
No.
potatoes are not there in the other location.
Right.
So when you do try to do a plus 1, it will just be 0 plus 1.
Right.
So how will that go?
Right. So maybe so at one location you had 2 potatoes, on another location you had 1 potato, and later when you merge, it's kind of funny someone is buying 1 potato. Later when you merge, maybe you end up with 3 potatoes. Right. So this is the custom merging logic that the programmer has to figure out how they want to merge. Right, but right. So this sort of completes our discussion on Dynamo itself, but we will continue to talk about this merging. Right. So Dynamo came out in mid 2000s, right? But it's a pretty landmark paper, right? And the reason why it is a landmark paper is because in academia people thought consistency is the way to go, right? What is the point of designing systems which are not consistent, right? The only reason academia thought about ever diverging away from consistency was because of situations like Git, right? When you have disconnected operation, right? So I am editing Google Doc in a plane, you are also editing Google Doc, and later when we later merge, so hopefully we can merge some meaningfully, right? So situations like Git, Google Doc, where you have disconnected operations, that is the kind of things that academia was thinking about. But in general, when you have a production data store, we always thought that consistency is the way to go. Why would you ever design a system which is not consistent? But this Amazon came out and said like actually availability is the way to go for many use cases, because we just don't want downtime, right? If someone wants to add a potato, let them add a potato, right? So this came under this started being called eventual consistency, and you will hear this term if you work in distributed systems. So the idea is we are not immediately consistent, right? So we may be inconsistent for a while, but hopefully eventually we converge, right? So eventually we are consistent, right? So many systems, whenever you want availability, you may want eventual consistency. So in particular, and by the way, yeah, so this Dynamo was being used in production. It was handling Amazon cart even on Prime Day, which receives 3 million requests a day according to the paper. It is probably now a lot more, right? And it heavily influenced Cassandra, another major data store, open source data store. But academia got quite interested in this problem, that how to do the merge without involving the programmer, right? So this is the holy grail, right? So if I can live with inconsistency, then I can get very good performance, because I don't have to wait and stuff like that. But the problem is it makes programming quite messy, right? So can we just deal with this inconsistency without having to involve the programmer, right? So somehow your language just deals with this inconsistency and the programmer doesn't have to worry about it.
So while designing an application, what would be the main focus, like consistency or availability?
It depends on your application, right? So for shopping cart, for instance, they chose availability because it doesn't matter that much. But if you are a bank, then you would like consistency.
Anyway, there would be a trade-off. We can't be.
Yeah, so you have to think about your application and choose the appropriate data store. Right, so there is this problem in the shopping cart. So let us say my shopping cart had one onion, right? And then I add a tomato, right? So now I have a tomato and an onion. Then I remove onion and I am left with a tomato, right? On the other side, I add a potato, which is triangle. So I have now a potato and an onion, right? And I try to merge. So far, we have discussed the way to merge a shopping cart is just to take a set union, right? So if we take a set union, I end up with one tomato, one potato, and one onion, right? But onion was already removed from the shopping cart, right? But when I did the merge, the onion magically appears again in my shopping cart, right? But this is the semantics that Amazon implemented, because for them, maybe you want to buy an onion, right? If you didn't want to buy an onion, you can remove it again. It's okay. But this is what academia has been thinking about, like, why did we have this onion again? We didn't want this onion. So basically, we want to, we have been trying to come up with some data types, right, which have meaningful semantics, right? And maybe for this particular example, let us say we don't want to forget about deletes, right? Because this forgets about deletes. Right. So academia defined this notion. Let us say there are two replicas, and they have two different states. So what we want is that these two replicas can merge automatically, right, without involving the programmer, right? And when they merge, they come to some state S3, right, which is identical, right? So we want to do a meaningful merge. We want to do a meaningful merge, and we want to do it without involving the programmer. Right. So, any thoughts, questions so far?
Sir, database that focuses on consistency wouldn't allow these workers to diverge.
Right.
Does it?
First they add everything, then you but like not restore the state.
Right.
The union should be done where the merge occurred,
Union should be done where the merge occurred.
and then the
So merge occurs here, right? This is where we are doing the union.
initial split occurred, where R1 and R2 end up in S1 and S2.
Uh-huh.
So that first we have to like merge those two, and then
No, but S1 and S, say that again. Yeah, that's what we are trying to do. We are trying to merge S1 and S2. So S1 is this state, S2 is this state. We are trying to merge and come to S3. Okay, so so first of all, this convergence is not really guaranteed, right? So it may happen that I think x is 2, you think x is 3, we exchange some information, and now you think x is 2 and I think x is 3, right? So convergence is not really that trivial, right? So we need to define what we want, right? So we want what is defined as strong eventual consistency. Right, so this basically says that the replicas should converge, right? Replicas converge. So note that this is different from sequential consistency. Let us say we are doing these two operations. So we have a set, C1 and C2 are adding values E prime and E. C1 is removing E prime and C2 is removing E, right? So from the sequential consistency point of view, there are two possible outcomes, right? What are they? So maybe this was the order in which the execution happened, right? If so, then the outcome is empty set. Right, and okay, so I drew this wrong. Right, so this overlaps with that. Then the other outcome is that add happens, then the move happens, then add happens, and then the move happens, and then the outcome is E prime. Right, so sequential consistency allows two possible outcomes, but in case of our shopping cart, add E adds E, then the move E prime makes it stay at E, add E prime adds E prime, remove E lets it stay at E prime, and when we merge, we might merge to E and E prime. So this is SEC, right? Because after merge, both our replicas have converged, right? But this is not SC, right? Because the only possible outcomes from SC were either empty set or E prime, right? So these are different concepts. So in eventual consistent systems, we are only interested in convergence, right? And we would like to do them automatically without involving the programmer.